am sharing. So let me do this. I'm unable to see the chat. So if someone has a question, please feel free to stop me. If I'm addressing it in later slides, I'll let you know, and we can talk about it when I hit the slide. So welcome everyone to our 46 meetup. Today is January 17th, 2023. Happy New Year. We can still say Happy New Year, I think, although it's like more than a couple of weeks already. This meetup is sponsored by Qualcomm, WRD software, which I'm part of. So thank you, Qualcomm, and especially Charles for supporting the meetup for 3 years. So that's a huge thing for us. The agenda for today would be just beside the welcome slides that would help new people joining. We would have the main and only topic today would be the yet another coroutine talk. There's a lot of coroutine talks, and I decided to have another one, hopefully helping people to understand how it's being done and how to use it. This is C++ 20 and beyond topic, so it's a bit on the advanced side of things, but hopefully I can make it simple for everyone. Polymorphic arrays, which I'm kind of want to talk about. It's a small 6, 7, I don't know, 5, 6, 7 slides. What's gonna happen next week? If you are new to the meetup, welcome. Super happy to have everyone here. Thank you for joining. If you're watching offline, thank you for watching offline. If you want to have a topic, by all means, just contact me and I'll help you to come up with a topic if you don't have one. And I have like millions of topics every week that I wish I could I would have time to have slides on, but I don't think topics are the problem. We just need time for the slides. But yeah, I can help if you wanna have any size of talk, from lightning talk, few minutes to a full blown one. Let me know. It's a good opportunity and it's really casual. We're all learning. No one here is an expert, so it is not myself and like an expert. Like we're just learning, everyone. So that's feel free. It's really casual. Again, sponsored by Qualcomm, WRD software, which I'm part of. Thank you, Qualcomm. And we have the regular stuff. We have Dropbox links. We have the Slack channel. Almost not using it. Discord, which I'm usually use for announcements. Ask me for a link if you want to join. SDCPP meetup. That's the YouTube channel, which we have the sessions uploaded. The San Diego C++ Meetup Twitter account, which you see here on the slide. This is the handle, and I have my own handle. I don't have Mastodon or anything like this. As of now, I'm just lazy to kind of transfer my entire life from one platform to another platform. Martin's Robot blog, which I have a page there, and I am planning to have a CoRoutine blog post that would be based on this talk. So it is planned soon, I promise, Martin, and I'll do that. Okay. Any question before we jump into the main topic for today? I have about 60 slides. I want to finish it less than hour and a half, hopefully an hour and a bit. So let's see if I can make it. Any questions? Let me see if anyone on the chat has anything.
Okay. Hello, I have a question, guys. Can
Yeah.
you hear me?
Yeah, we can hear you.
A friend of mine, Yining, he wants to come in, but he's waiting for the approval.
Oh, okay. Okay.
Okay.
Give me a sec. We'll do it in real time.
Hey, copy. I'm here. That's
Hello.
some connection issues. Hey, hi everyone.
Okay. Yeah, I can see two people that are waiting. I'm sorry, I need to kind of throttle that because I had the issue that someone actually hacked to this account, not my account, but just hacked somehow, and it wasn't pleasant. Okay, so it is approved, and please let your friend know that they can join now with the link, the team link. Thank you. Sorry, I try to make sure that I have everyone approved just before, but I looked at the link like half an hour ago, so it's pretty new. Any other questions before we dive in? Okay. So yet another coroutine talk. There's multiple of them. Now, one of the things that actually triggered this talk was a blog post by Pablo Arias, which he is from Munich, and I had the pleasure to kind of had a chat with him, kind of offline through emails, and he agreed that I'll use his ideas here from the IO U-ring, that it's a kernel feature, and I made some changes, so you have opportunity to read the blog post. It's a 3-part blog post. I think it's a great one, by the way. Um, and also, I'm introducing some new kind of complementary kind of approach that you can tie together. So he's looking at read asynchronously, and I'm doing writes. So you would have the both of the sides. So thank you, Pablo, for this great blog post, and uh, this is a great one, by the way, if you wanna read about IO, U-ring, and coroutines, which we're gonna talk about today. Another shout out would be there is a great series of blog posts uh, from Modern's CPP, Rainer Grimm, which I highly recommend picking up. He has multiple stuff. First of all, I have these books that I that's took from Amazon. So this is a new book, the Core Guidelines, which I highly recommend. There is CPAPAS 20 um, book. He has multiple ebooks that talks about CPAS 17 and 20, uh, the regular like the regular features, and he has a very specific ones for multi-threading also. Um, he has an educative .io class, and is really famous in his CPP Con and other talks. So highly recommend kind of picking up his work and read about it if you want to learn about C++. You can
Excuse me,
subscribe.
Kobe.
Sorry.
Sorry to interrupt. Sorry
Yeah.
to interrupt. But I just can't see the books you're showing. Can you make it
You,
bigger? Command
these
plus.
books, the one
Yeah,
on.
yeah.
I
It's
don't
too
think I can
small.
make it.
Really
I
small.
I I'm sorry. I can't make it
No
bigger.
zooming option there.
I don't think so. Let me
Are
see.
you using Mac
Uh,
or Windows?
okay. Here.
Here we go. Here we go. Thank you.
Okay. Sorry. Is this looks better?
Much better.
Okay, awesome. So, by the way, you can always contact me if you have any question regarding. Okay, hey, Kobe, you talked about this. Can you? And these slides would be published, so don't worry. So you'll have the slides.
Okay, believe me, I'm about to drink some coffee and I'm gonna hit you with a lot of questions. So be prepared, Kobe.
Sounds good. Okay, let's dive in. Okay, I have few disclaimer and clarification. First of all, it's a complicated domain. I'm not an expert. Okay, so you might ask me questions. I say I don't really know. I need to go and figure it out. It's a big domain. Uh, it's one of the things that I needed to really spend a lot of time, delve into the details, try out all kinds of things, and it takes time. Uh, the code that you see here, it's a very simple code. It's in GitHub. You can go and build it with CPAPAS 20 compiler and just breakpoint, just hit breakpoints and just take a look at what you see in the debugger in order to understand the flow. It really helps to understand coroutine, in my opinion. So there are all kinds of small things. I'm not talking about exceptions. So there is exception part of coroutine. I'm just not talking about it. It would just increase the slide deck and I didn't think that it's important for now. Uh, I'm not explaining about every single customization available for the design. And there are all kinds of ways to achieve the same, like you can inherit from a specific class or structs, you can return values. I'll talk about it when I hit that. Uh, it's not completely comprehensive in terms of like, because it's a very big topic. I'm not talking about CPP Core, the GitHub project, and other frameworks. You do want to take a look at them. I'm going to show the vanilla C++ 20 coroutines and how to use it if you want to use it yourself instead of relying on an external framework. You should, by the way, look at external framework, and I'll tell you in a moment why. Uh, as I mentioned, try it out. Use the debugger to step through. There's a lot of magical stuff happening. Uh, Using the debugger tremendously help, in my opinion. Okay, so let's delve into CoRoutine, and some of the definition here are kind of loosely, kind of it's my definition, it's not the standard definition on all. I just wanted to make things simpler. So a coroutine, it's a special function, and the way it works, it looks different from a regular function. So a regular function, there is a flow, and I'll show a diagram, and it's really different. And you need to, first of all, need to understand that you're looking at code that would behave or would run differently. It's not going to be, and it's not even threading related. It's very different the way it's being handled. There's a lot of magic. They call it compiling magic, but it's not about compiling magic. It's about the compiler would inject all kinds of instantiation of classes and jumping from one code block to another code block. There's all kinds of stuff the compiler is injecting. Hopefully by the end of this session, you'll understand how it works and you can take it further to the next level. Um, I'm going to talk about suspend, resume. I'm going to make some comparison to threads. Maybe it would help, but it's very different from threads. So what is the challenge in understanding coroutine? At least my challenge of understanding coroutine, and I attended a few talks, a couple of them in CPPCon, and I felt like some of them were missing some stuff. First of all, there's a lot of new keywords, and yeah, it's a lot of work for the speaker to kind of go over all the keywords and explain, and it's really tedious. By the way, if you go to CPP reference, it's really tedious to understand exactly what each keyword does and what does it mean when you use specific keywords and all. But the basics were kind of missing, in my opinion. There's a lot of new API and new interface that you need to be aware of, and you need to understand how to use it. Some of it you can implement, some of it you can inherit. I'll show examples how to do at least one choice, and you can understand how to do the inheritance part if you want to. As I mentioned, there's a lot of compiler magic injected implicitly, and we need to understand that. We need to explain at least for the simple examples how things are jumping from one code block to another code block. So there's a new code flow that you need to understand. Oh, the compiler would jump to this specific code and then go back here, and there is no actually threading involved. It's not because I'm actually in kind of starting a thread and waiting on a thread. It's not really happening with threads. It's just different. It's like instructions that are jumping from one block to another block. And one of the things that I was confused of is like, okay, what does it mean suspended? Where is this context kept? Who is actually allocating the context? Where it's being actually executed? Like what? And when we talk about execution, is CoRoutine actually providing like a threading mechanism? Like there's the thread pool that like this CoRoutine is running on? All these questions, by the way, no. The question is no. There is no threads that are being spawned on your behalf. No, you need to understand where the context, which thread is running the coroutine and suspension and resume, all of that, you control that. So it's not like there is an underlying mechanism of threading that would do all this async behind the scenes. No, that's not happening. So where is the context of each code in terms of threading was very confusing, at least for me, and I wanted to understand how I can control that and how it's being done and customized. So that's something that I think was a challenging part, at least for me, and I want to kind of help you with that. There are coroutine functions, there are coroutine objects. It's kind of confusing a bit. We'll talk about it. That's another thing that might be a challenging part when you first introduced to this framework. We'll talk about what is coroutine function, what is coroutine object, what is the handle that you'll see. This whole thing would be hopefully clear by the end of this session. Okay. Yes.
I was going to ask by coroutine function and coroutine object, and feel free to tell me that you're going to talk about this later. Do you mean do you mean stackless versus stackful coroutines, or is this something different?
It's something different.
Okay.
Something different. I'm not actually talking about the difference between stackful and stackless coroutines. I've seen that, but I'm not actually talking about it in great details. So I can remember. I have a slide that might mention that. I can't really remember. By the way, this is the first time I'm actually providing this talk, kind of presenting this talk, and it is a very kind of a challenging topic. So hopefully the next time if I have it next time, it'll be kind of more in a better shape. Let me tell you what Bjarne actually is saying. So Bjarne has this a tool of C++, the third edition, where he has a C++20 coroutine section. And this is actually, I have the ebook, and I just pasted a very tiny section of it. I strongly, and there is a generator, we talk about generators, section. And Bjarne says the following: I strongly encourage you not to write such code yourself unless you are a library implementer trying to save others from the bother. If you are curious, there are many explanations on the web. By the way, I really like if you're curious, there are many explanations on the web. By the way, there's a lot of stuff on the web. Let me tell you that. Um, uh, and this is something that I've seen a lot, that people say it is kind of complicated, and I'm not actually mentioning here performance at all. So I'm not testing performance. I'm just my goal is for you to have better understanding of how coroutine works. And so the what you usually hear or read on the web is that C++20 provides a very low level ingredients. I would say even like, this is my term, by the way. It's like, I don't know if this is correct, but it's like an assembly of coroutine. And the idea is that either people, for example, Louis Baker, which is very famous individual in the community, has this CPP code that a lot of people know, 2.6K stars. And the idea was that this assembly coroutine, which provides the very low level ingredients, would be used by library implementers, and they would provide us the kind of upper level interface, hiding a lot of the boilerplate code. And you'll see there's a lot of boilerplate code that you need to write and understand. But again, my goal is for you to understand the mechanism. We'll show examples, and from that you can go into kind of, you move up to higher layers and with better understanding. So if you go and just Google or Bingo, whatever your favorite search engine about C++ coroutine, I found in images, I found two images. One is from Rainer, modern CPP. This is the one on the right hand side, and one from Stack Overflow. So let's start with the right hand side. So a regular function, a caller called a function, it runs to completion. There are no threads, nothing, right? It runs to completion, returns, and the caller continues. In a coroutine domain or coroutine space, this function, it looks like a simple function, but it's basically a coroutine function. You can suspend the function. The caller would gain control back and would continue and may resume the function. Function might be suspended again as many times as it want to. So the idea is that the coroutine is in a suspend mode. You, as another entity outside of the coroutine, can always resume it. Like you have something that you hold in your hand that control the coroutine in terms of I can suspend the coroutine until it's destroyed. And once it's destroyed, everything, the context is destroyed, whatever is was allocated, everything that is associated with the coroutine just get destroyed and we continue. This is an example of just two coroutines kind of calling each other. So A called B, B resume A continues, A resume B continues, resume A, and so on and so forth. So that's just the two coroutines kind of suspending and resuming each other. Okay, so this is very simple idea. If you think about it, forget about the implementation details. It's a very simple idea. I have a function, something that looks like a function that I can suspend, like in terms of the instruction, it's suspend, and then the caller continues. But someone takes care of keeping all the context, all the state of this function somewhere. Okay, it's taken care of by the framework. The compiler is doing a lot of work to do that. And when I resume, everything continues as if it was because the context is there and it looks like a regular function. But when I suspend and like I exit the function, I'm really not exiting the function. The function is just in a suspended mode, and someone is keeping all the context for me. So what I'm gonna do the following. I'm gonna talk about some of the main high level principles that they would help us to understand the future code. So there is a lot of code towards the second half of the talk, but this part we just need to go over the details. If you miss some of this stuff, don't worry. When we get into the code itself, things would be hopefully much cleaner and clearer to you to understand. Okay, so what does qualify a function to be a coroutine? So there are keywords. If you have a co-await in the function, it is going to be a coroutine. If you have a co-return, it's going to be a coroutine. Same for co-yield. Co-yield specifically, I don't know if that's 100% true, is used for a generator use case. So I'm going to talk about two use cases. One is a generator use case, and the other one is a non-generator. I don't know what's the other term, but it's a non-generator use case. I'll start with the generator use case because it's easier to kind of digest. So co-await expression, this is where I can say co-await something. I suspend that execution, and then someone that holds a specific handle to my coroutine object can resume my execution. As I mentioned, co-yield expression supports generator functions, and I can have like infinite data stream. I can return new value each invocation. There's like almost every C++20 coroutine example would have some type of generators. It's easy to demonstrate, so I'll show that. There is the proposal N 4402, which is describing the design goals. I'm just gonna briefly mention that it needs to be scalable. They want to have the design goals was I want to have billions of concurrent coroutines. Again, I'm not testing here any efficiency, performance. This is not part of the goal of this talk. We want to have efficient resume. We want to have efficient suspend compared to the cost of overhead of function, overhead of threads. You want to minimize the overhead, the overall overhead as much as possible. That was one of the design goals. You want some machinery that allowing library designers to develop coroutine libraries, exposing all kinds of high-level semantics. Generators is one of them, for example, tasks, all of that. So that goes back to, this is basically the assembly of coroutine, what C++ 20 provides us in some goals to have people writing libraries that would allow us to be on a more high level. It should be usable. One of the design goals, it should be usable in environment where exceptions are either forbidden, they're not available. So the idea is to have exceptions. Again, I'm not talking about exception in this talk, but this one was one of the design goals. Okay, so the framework. There's a lot of functions to support you as a coroutine, either library author or user of coroutine framework. The design, they went out of their way, the designers of this feature, to have the whole framework fully customizable, which means that we can customize almost every single point. For example, I want to suspend the coroutine. So I want to run something when I suspend it. I want to resume the coroutine. I want to run something when I resume the coroutine. Like, they actually had all kinds of points where you can do stuff in critical parts of the coroutine machinery. So for example, you'll see that I can create a coroutine object when I create the frame, and I can decide if I want to suspend or resume the frame when I just created the instance of this coroutine frame. I'll show that in generator, and also generator, it's pretty obvious. So this is very important. I think one of the keys to understand like how to actually use coroutine is to understand that there's a lot of functions and semantics that helps you to customize how you want your framework to behave. So that's a very important thing. I have tons of examples, so don't worry if it's not really clear right now. Promise objects is another thing that actually confusing, because you see it's nested sometimes in something that is a coroutine object, let's say task or a generator. A promise object is a transport, or a kind of a means to communicate result back to some waiter. So the idea is that, like the overall idea is that coroutine is a way for me to suspend execution in a specific flow. I going back, and someone is doing some computation on the background. Again, I'm not talking about what is the context of the thread that is being used to do this computation. I'll talk about it. But the idea is that some computation is happening and I need the result back. So the promise object, and probably promise is not the first time you hear it, but promise. The promise object is an object that it's actually a type, a class type that you write. You customize it how you want it to behave, and it is using to communicate back the results to someone that is waiting on this result. The coroutine frame holds the state of the coroutine function. So as I mentioned, think about the function. The function we entering a function and exiting a function. This is something that we don't know or we're not aware of how to do that until C+20 when we have coroutine. So because when when we exit the function, the stack frame is gone, like it's winding back and all the state of the function. This is not a regular function, so there is a context. The coroutine frame is where the context is held. Okay, let's continue. Promise. It gives us the result. It also handles exception. Again, I'm not talking about exceptions in details here. That all the work that was done as part of the coroutine function, and it's that simple. I'll show a lot of code, so you'll see that. It is mutated from the coroutine function itself, which means that when I actually trying to do co-yield and I have a co-return, the result are actually, there is kind of, it looks like a communication channel between the coroutine function and the promise, and then I get the promise value back and I'm done. It sounds very complicated. It is kind of magic, but this is something that we'll talk about in detail, so don't worry about it. As I mentioned, lots of customization. You can control in the promise. You can control, is the coroutine should be suspended? This is the initial suspend, or when it ends, final suspend. So basically, the promise itself, which lives in kind of a task, has few functions that you need. It's an API that you need to implement. Initial suspend, final suspend are two of these functions. There are more of them. And these are a way for you to customize how your coroutine function behaves. For example, initial, when you create the frame, do you want the coroutine to be suspended? And I'll show in generator that the case is yes. Why? I'll show why. And you can and then you can write code that does something, maybe doing some initialization and so on and so forth. Same deal for final suspend. It's a way for you to write code before we destroy the whole coroutine frame. So there are opportunities for us to do all kinds of work when the coroutine function starts or when it's being destroyed. Unhandled exception, handled when when exception happens. I don't know why unhandled exception. By the way, I can remember why this wording was chosen, but it is invoked when exception happens. Get return object, another API that you need to implement. And one of the I think most confusing part of when you read code that is dealing with promise, get return object actually construct a task from a promise instance. So try to imagine, I'll show code, try to imagine there is a class, let's call it task, that has a nested class inside, which is the promise. And get return object is a function that the compiler is invoked. By the way, the compiler is invoking the initial suspend on our behalf, final suspend. We don't invoke that. These are customized checkpoints that the compiler is invoking. Like if you put a breakpoint in initial suspend or final suspend, you see that someone is calling it. I didn't call it. There is no thread. It's the framework that is being invoking that, this is where the magic happens. There's like something that we are not really used to, that all kinds of API are being invoked, and we don't call it. It's like the compiler is injecting the code. So the compiler is injecting code to create this task that I mentioned. It is calling get return object, which basically construct a task from a promise instance. Again, I'll show code. I think this is one of the more confusing part, but I think code would help us. And then the return value or yield value in terms of generator. This is kind of another confusing part, which generators have a different API the non-generators. Yield value basically assign a value that would be going back to the caller. And in generator, we'll see an example. Return value is a value that goes back to someone that is waiting for that was suspending the coroutine, and now some result is available and goes back to the caller. It's magically being invoked. That's why I'm saying it's, again, all these functions, you don't call it. All these functions, you don't call initial suspend, you don't call final suspend, you don't call get return objects, you don't call return value. By the way, my opinion, set return value would be a better name, because it's actually setting the return value that we're going to be back, communicated back to the waiter. Same deal for yield value. It's like set yield value, set value that's going to communicate back to someone that holds a generator. So all of these functions, you don't invoke them. The promise usually would hold your result. It may be a struct with few types with values. It might be maybe a single type, maybe an integer that you computed and you want to communicate back to a caller, to a waiter or caller. So usually the promise would have information that you want to communicate back to someone that is waiting. Okay, so this is the last slide before we see code that will make things much better. Yeah, someone is asking something.
Yeah, I was just going to comment. I think it looks very similar to std packaged task.
I don't think so. Wait a bit. Std package task is very simple compared to the mess that we have here in Coroutines. Okay, wait a bit. And like package task give me something that I can go and run on a thread, right? And then I have a promise and all. I think I understand where you're coming from in terms of but it's like I can make sense because I can trace back like who called who.
Right.
Not in the case of coding. The thing that actually was very difficult for me is that all this API, and wait for the next slide. The next slide would show kind of a pseudocode of this API. They are invoked out of a thin air. Like it's not me invoking them. It's the compiler injecting code for that. Okay, so it's different in this sense. Like in terms of package task, if you have the result, you set the promise, and someone is holding a future, right? And you good. Like you can see that you can make sense of this logic, but it's different in coroutines. Okay. A recap. So get return object is important. I'll show why. It creates the instance. It actually creates the instance of where the promise lives in. It has a handle. I have a pseudocode in a moment. It communicates back the results, either if we're talking about generator or non-generator, like regular. And there are actually 3 APIs that you need to implement one of them. One is yield value generators, return void. There is no actually work that has some result that I want to communicate. It's void, just look, returning void or returning some value. Okay. Again, if I would need to name the API, I would say set return value and set, because that's actually what happens. Like the value is being set, populated in the promise, and then the promise can communicate that back to the caller. Yeah, I already talked about initial and final suspend. They have a special meanings. And then we'll see what is awaitable that you actually co-await on. And when we see examples, it will be much easier. So this is what I try to do is to come up with a pseudocode of how your coroutine would look like. Okay, so this would be a coroutine that you might write. Again, it's all pseudocode. You have a co-wait on some awaitable. and a co-weight on that can be 1 and 2, by the way. That should be 2, by the way. Co-weight on another awaitable. So what is awaitable? We'll talk about it. It's hinted here. And then I can communicate the result back to someone that calls the function. Okay, so let's talk about this task that you mentioned. So there is a task here, which is basically it's going to be a class. It can be a struct, of course. The most important thing, it has a coroutine handle inside. So this is your gateway. This is your key. This handle is your key to actually control the coroutine. If you're holding this handle and some API would provide, the compiler would pass you the handle, you can control this, the flow of this coroutine. For example, if you hold that and you want to resume, this handle has an API that has a function, a few functions that you can actually call resume on this function or this handle. So, so this is a very important attribute in the task. Inside the task, there is a type name promise. It has my result. It can be an integer, it can be a struct, it can be anything that I would like to communicate back, or void, like nothing here if I have nothing to communicate back. I just did some work and I said, okay, I'm done with the work, but there was no results, so it's void. Then we have initial suspend. We have final suspend. Remember, these are two checkpoints that I can write code inside this function. The compiler is calling that. Compiler is calling initial suspend when task is being created, when this whole thing is being, this coroutine frame is being generated or allocated. The compiler would give me opportunity to do some initialization. It would call initial suspend. When this frame is distracted, let's say when I return from using CoRoutine of the result, I have opportunity to run code in the final suspend. And I can tell the compiler, by the way, after I did this initialization, please suspend the coroutine. Or after I did this initialization, the coroutine is not suspended, it continues to run. And the coroutine would continue to run until it hits maybe co-wait or co-return. But I have the power, I have the opportunity to tell the compiler how I would like this function to behave by fulfilling this, implementing these functions and returning a very specific return value that the compiler would understand and would act upon in order to know if it needs to suspend or resume when I create the task, or maybe when I destroy the task. Now, I'm talking about this task that is being generated. Someone needs to create this task. This is where getReturnObject kicks in. The compiler would invoke that, and I need to return, when I implement this getReturnObject, I need to create this task for a promise instance. And I'll show an example. Again, it's a lot of boilerplate code. It's really like an assembly of coroutines. So if you are a library implementer, you would probably going to hide this repetitive kind of code that people they don't need to be aware of. And then I need to implement how I communicate the promise results back, either through return value, return void. It's like set value, set void. This is, I think the return value and return void is like not best names in my opinion, but it is what it is. Now, when I say I want to wait on some awaitable, like I created the task. Okay, so the task is created. So I created this task, I created this frame. There is a promise living inside. So the mechanism is ready. Now we can start using it. So when I say co-await on some awaitable, this is basically, I'm creating a coroutine function object that has an operator of co-wait. This needs to be a co-await, not co-wait, but co-await. And inside, I have a struct that I'm defining that I'm gonna return back this is kind of an operator or co-await that returns an auto. We'll show an example. It's going to be much easier to understand. And inside this awaitable, I can have maybe a context that I need to maintain. It's a regular struct. You can have whatever you want inside. But there are three important APIs that you need to implement. First of all, the compiler would, when a compiler hits this co-await and it creates this object, and you return a waitable from this co-await, you needs to return this awaitable. It has an API. The compiler would use this API. The compiler can ask this API, are you ready? Maybe you're not ready. Maybe you need to do some stuff in order to be ready. You might tell the compiler, look, I'm not ready. I need you to suspend me. And it's going to be suspended here. And whoever called the function would continue and the function is suspended. Okay? Now the compiler needs to know what happens when you suspend this awaitable. Do you need to write any code when this part of your logic is suspended? Do you need to execute any code when someone that holds the coroutine frame says resume? Do you need to run some code? So these are, again, customization. On one hand, it's customization point, but it's also a way for you to communicate to the compiler to generate code how your code would behave and run. Are you ready? When someone called co-await, are you ready? Maybe you're not ready. Maybe you need to go and compute something. So you ask the compilers to suspend because you need to do something on the side, maybe in a different thread. We'll talk about it. And then if you say, I want to suspend, the compiler gives you an opportunity to run something before suspending. And when someone holds a handle and tells you, I want to resume, you have opportunity to tell the compiler, okay, I want to run this code when you resume the coroutine. So this is why I'm saying there's a lot of customization point, and you need just to be aware of them in order to write something meaningful. So I did my best to give you kind of a pseudocode of how the structure in general would look like. It's very similar to generator. The generator has less code, but it's the same structure. Just to recap, you have the function that is a coroutine function. It has a co-await and co-return. So it's enough to have co-await, by the way, or co-return to nominate this function as a coroutine function. You have a task that has a promise nested in it. The task has a handle to the coroutine frame. It's a very important attribute here. It is passed to the awaitable. So this function, this API, these functions, they get as a parameter the handle. Why? Because you can take this handle, keep it somewhere. Let's say you run your work on a different thread, and the thread is done, and you say, okay, I have the handle of the coroutine. I can tell the coroutine now resume because I'm done. So the handle is being passed by the compiler. Compiler is generating code, is being passed to the API, so you can use it when you want to control the flow of the coroutine.
So,
examples would.
I have a question. Can you hear me, Kobe?
Yeah, I can hear you. Go ahead.
So there is a conversation happening between the compiler and the code, and that all of it happens in the coroutine function object. Is that correct? The conversation between the compiler and the code, asking, do you need to run any code after I suspend?
Yeah.
Is that
yeah?
something close to it?
So the way I see it is that I have three things that I need to be aware of.
Yes.
And they are talking with each other at some point that you really need either to break point to understand how it's being done, or after you do it a few times, you already it's all your brain is already kind of
Yes.
understand how it works. So there are 3 points. The task, which has a promise that has initial suspend,
It's a
final
class.
suspend, get return object, which actually creates the task, and then communicate back the result with return value, for example. Then you have
task function.
yeah, you have the function itself, the coroutine function itself, where you have the logic. It looks like a very simple, but it has like these keywords that might do something that you're not used to in a regular function, like suspend the function, and then the caller of function. Function is just a function. Someone in main function just call function. Halfway to the function, main continues. It's
So
very weird, right?
So let's call so some awaitable number 1. That's the function 1, and then
Yeah.
there's a some awaitable number 2.
Yes.
Right, but it's here that is like a bug here. Okay, so
Yeah,
it says
there
1 on
needs to
both.
be
Okay.
2, and I would have another type
slide
for awaitable 2. I would have another type here, and I'll fix the slide so it's fixed and makes more sense. But yeah, this would be corresponding to one type. Instance would be created of this type, and I can have another type and another type. They do different stuff. They do different work.
Yeah, and they get suspended at certain points, right?
Yes.
To let the other ones, like a function or a type, let's get a type is going on, and then at some point can be suspended to let B, the type B, to keep going, and at that point it might get suspended also to let type C to keep going.
Yes.
And that's
but remember that
wow,
in order for in order for some awaitable 2 to be executed, I need to resume the coroutine. So I have a master function, coroutine function that has a handle, and I'm suspending here. I must resume it somewhere to go into the next co-await. If there is a next co-await, doesn't have to be, but if there is one.
And then at some point, the co-return will get the result and return it to us as promised.
Yes.
And then we'll use it. So, by the way, Kobe, it would be very useful if you find like some real case uses for this kind of code. I know it's new, C++.
Oh, wait. There is.
Really cool.
We only in slide 20. I told you I have. There is a very very good use case for this whole thing, but just wait for that. I'm actually almost done with the text. There's gonna be code. I already talked about coroutine handle, super important element. It enables the caller or someone that holds it to control resuming, suspending, and as I mentioned, the awaiter has await, suspend, and there is a parameter of the handle. And magically, the compiler passes an argument of this handle to this parameter.
The argument, some of the arguments are written by the compiler.
They are passed by. I'm not passing it. Like await, suspend. I'm not actually this await, suspend here, which gives me opportunity to do something when the compiler is going, or the runtime is suspending this, actually saying compiler and runtime interchangeably. Sorry about it. But the runtime suspending it, I have opportunity to do something, and I'm getting a handle. The handle, I can keep it somewhere. I can pass it to a thread. The thread is doing work. And at the end of the work, it's doing that resume on the handle that I passed to this thread.
Yes.
And magically, this function would continue to run. Which context we'll talk about it, because it might be confusing, because I said main is continuing. There was no, like, there is, we're not creating
another function.
We're not creating threads from a thin air. Threads needs to be, so.
Yeah, great. Gotcha.
If I may, this reminds me very much of like a range iterator. The compiler provides syntax for variable : container. That syntax maps to a number of API calls that must be implemented by your container if you want to be able to use it that way. This seems the same thing. If you want to make something that can be used by the coroutine keywords, you implement these APIs.
Yes. Yes. Actually, what's your name?
My name is Sean.
Hey, Sean, you're bringing a good point, because I was about to say, I was planning to say that, yeah, coroutine, a lot of people kind of complaining there's a lot of API, and it is a complicated topic. Hopefully less complicated within an hour. But you're right, like it's not different from other um, other types of or mechanism. I'll take something very simple. You don't call a constructor, like you don't really call the actual constructor. Like if you do new, like some function is on your behalf. I know I'm kind of simplifying some stuff, but or like you don't write some functions, but the compiler, like the rule of five or whatever, the compiler is writing for you, right? So I know I'm oversimplifying it. What you mentioned is also true. It's just this whole idea, it's kind of on steroids. There's a lot of APIs. They are very, very important. You need to understand what each API returns. The return types, the return values of these APIs are really important. They mean something, and you need to understand that.
All right.
Coroutine frame, it's internal. My understanding, it's heap allocated state. I don't know if it's always heap allocated. I don't know if it's mandated by the standard. I can't remember actually.
It is not mandated by the standard. The compiler will make its own decision.
Okay, thank you. Okay, thanks for that.
But it may always be allocated. You cannot ever guarantee that it won't be heap allocated.
Okay. Yeah, I remember a lot of discussions long time ago about this topic, and I couldn't remember what was the actually wording. So thanks for letting us know. Okay, so it contains a promise object with all the context that or the author placed in. So I'll show you what I'm doing with a promise object. Okay, let's start with the generator, because that's easy. Okay, so the promise is going to create it in the coroutine frame. Initial suspend, you have either suspend never or suspend always. So remember, I have checkpoints where I can tell the compiler, when you create the frame, I want you to be suspended always or never. In generator, I want to be suspended because I'll show you what I'm doing. And then I'll have a function that I'm writing, get of the generator. It's going to be invoked, and I'm going to resume, suspend the coroutine. I'm going to use co-yield of the value, and the yield value of the promise, the API of the promise, would be invoked. It's like set, and it's going to be returned from the generator function from the get. And then it's going to be suspended, get will be invoked again. And I try to capture that in some diagram. In general, that's what would happen. You create a generator instance. I'm going to have a function, I call it compute. It's a coroutine function that returns a generator. It has a co-yield. Remember, this compute function has a co-yield. That's it. It is doomed to be a coroutine. And what I'm going to do is, when I create the generator, the initial suspend, I want to return suspend always. So basically, what I want to do is create a generator, hand it off to whoever called this compute function. It's going to be a return value, and now I'm suspended. The user has now an object that can invoke a function. In this case, it's going to be get. This get would give me back a value. I'm going to have a resume because I want to compute the next value that would be given if I ask that get again. And I can ask that get as many times as I want per my specific implementation. The co-yield value is being actually triggering an yield value, which is a set value. And now, again, I'm suspending. And the get function returns some count, which is nested inside the promise. So I call it's a member. It's a data member that I created called count. So just to recap, I design my generator to be suspended as soon as it's being created. Now I have a generator at my hand that I can call get. I'm calling get. It's being resumed. I'm getting the value back. There's this mechanism of co-yield that calls yield value. It's being suspended again, and I can call it again and again. So when I do the resume, and I'll show you the code, this is where I have the opportunity to compute the next value. If I want to capture that there's a lot of errors, and every coroutine talk, by the way, there's lots of errors, lots of stuff like that. I'm trying, like I did my best to kind of try to explain that in a simpler way. This is the generator that I'm going to create. Sorry, there's a question?
Yes, Shad here. Is this similar to RNN, recurrent neural networks?
I don't know.
Have you heard? Okay.
I don't know.
Seems like
I heard about RNN, but it's being so like it's been like 2015
blowed
since
up. Okay.
So I'm sorry, I don't know.
No problem.
Okay,
it seems like it because where neurons kind of remember some of the information from the previous neurons.
Oh, I see.
Sometimes double previous or triple previous, you can get some information from steps that happened three steps backwards or 4 steps backwards. You can decide that. It seems like that. Okay.
It might resemble to all kinds of mechanism, but it's not exactly the same. Okay, so there are 3 elements that I wanted to highlight, and then we'll take a look at the code. The code actually is very simple, in my opinion, once you understand that. So there is a main that creates a generator. Just call a function called compute. So this is a function. This is a coroutine function calls compute that it returns a generator. When I call this function, generator is being instantiated. This class is being instantiated. There is a promise inside. It lives inside, okay? And I create a generator from main. I just call generator and I hold it. Now there is a loop inside this compute that has co-yield value. The co-yield value, it computes a new value. So next time the coroutine is being invoked, I'm getting a new value because it is computed here. Get would basically resume. I'll show exactly what does it mean, and the next value would be computed. When I do co-yield value, if you put a breakpoint on yield value of the promise, the compiler basically you'd see the compiler invoking that. When you say compiler, you'll see a chain of calls that actually invoke this function. Again, it's the same thread of main. There is no extra threads happening here. This is like the simpler case where there are no, like there is a single thread here. Yeah, so that's basically it. So let's take a look at code, because code is like, should be very simple. As I mentioned, I'm calling compute, and I'm getting a generator. So I'm getting something that I can call on this API. So this generator is something that I write. It's a type. This auto is basically a type. It's a generator that I write, and I could write it in many ways. A lot of ways that you'll see online. It's a template. So you see that as a template, and then I can just call that get, just getting, and in this specific case, it's kind of infinite times I can call it. So compute is a coroutine function. Why? Because we have co-yield. So I started with value 17. So first of all, when I'm calling this function, the interesting part, if you put all kinds of breakpoints, you'll see that this generator is being invoked. This get object is being invoked. I'll show you that. and eventually you'll get this generator object instance in your head. Now, this generator has an API that I wrote. Some of it is an API that I need to write. Some of it is something that I need to expose, and some of them are just my APIs. That get is my API to get a new value. The co-yield value, as I mentioned, would call this yield value that is an API on the coroutine task itself. And this is, so when I call co-yield value, it's basically returning the value back to the caller and it being suspended. Okay, so let's take a look at what's exactly happening. So this is the generator. I could make it non-template. If I just want to have an integer, I could make it here, but everyone you see it a lot in online that it's actually a template. There is a promise type inside. I'll show you the implementation in a second. This is the handle type, which is my gateway to control the coroutine. And the handle type is a member, data member of the generator. It's a struct in this case. I could make it a class. It doesn't really matter. So what is this promise? So this promise is a nested type, and this is the first time I think we see a real API. So what am I communicating back to the runtime? Initial suspend, when I create this generator, when I call this generator, this compute that actually creates this generator, I want the coroutine to be suspended immediately. I don't want the coroutine to continue to run. Okay, I just want to hold the generator and I want to do something with it later. Again, finally suspend. I don't have in this example where I suspend it because I've just Control C and that's it. But this cleanups, there is nothing here. I do suspend always. Nothing special here. The funny part is that you can see in the initial suspend, this whole purpose of this function, and again, there is a way to inherit from a specific type, but the whole idea here is to communicate back to the runtime, just suspend. When you create the generator instance, just suspend the coroutine and that's it. So this is a way to communicate that to the runtime. It looks funky, but this is the way. There might be other ways to do that. Again, there is inheritance that you can do, but that's one way. This get return object is the point of creating the generator from promise. This is kind of a boilerplate code. This handle type is a type def. This handle type is a type def. So the compile, if you put here a breakpoint and you call compute function, generator is being created here. So here's where we create a generator. And the generator has one member. It's the handle. So this is where we create a generator. Here's the yield value. Take a look what happened here. When I basically pass, it's not really me. I'm not calling yield value. The runtime is calling it on my behalf. It's passing this value to a member of the promise. This is count. And I'm telling the runtime, I want to be suspended. So after I yield the value, I want to be suspended.
Should that be, it says type int value. Would that be type T? Is that a mistake?
That would be type T. Yeah, you're right. This should be type T. Yeah, thank you. Thank you for noticing that.
And the suspend always is after you yield the value, suspend forever. This code never runs again.
And unless I call
on it
a specific function again, I'll show that.
Okay.
So what happened here is that co-yield value set the value, okay, that I can later extract and suspend it.
Yes.
When we get
so the value equal 10 plus.
And when we resumed, I compute the next one. Okay, it's a very simple, stupid kind of computation, but just imagine what you can do otherwise. and then it's going to be computed, and then the for loop would be, again, it's going to be suspended. So we get the next value, and it's going to be and we're going to suspend it.
So
I wanted to
question.
Yes.
Question. So yeah, go back to the value value plus equals 10, that line. Yes. So here this is a for loop. You're setting the value, co-yield value. Then the value used to be 17, but now every time the code runs here, it'll be 17 plus 10, 17 plus 10. Is it possible to run to have a base code that will suspend this particular function for 10 years? And then in 2033, again, it's called off on again, and then the computation is happening again until a certain amount of time. Is that possible?
Yeah, basically you need a trigger to resume this function.
You
need the trigger for that
function, function.
Yes, okay. And I just want to see if I have the actual. So when you call get, I'm going to jumping before the next one would be with the UDP and IOring. You know what? Let's take it one at a time. So when you call compute, I just want to show when you call compute and you put a breakpoint in the generator constructor, this is what you see. And it's funny because you'll see that it's like you're calling a function, but the debugger would show you like at the end of the function, because you're creating this generator and returning that. So this is what happened when you call compute. This is kind of interesting because someone is calling. You just called compute from main. I just called compute. There is nothing else that I've done. But this get return object is creating the generator for me. There is a constructor, and now I have a generator in main function. Now this generator has a .get function. Now what happened with this .get function? This .get function, when I actually call that get function, resume happening on compute. So compute is actually resuming. Take a look at the namespace and how things look like. I have actually more later for the UDP one. And yield value is being invoked, and then the value goes back to the caller. So from main, I just called get on the generator. So generator has this get, and resume is invoked for me. And actually, give me a sec, because I realize now that I don't have, 1 second. One of the important things that I'm doing a real time, but this is, I realize that I'm missing this. This is important one. So okay, this is important one. Okay, let's continue that. When I call get, resume happening, and I'm returning the count. Remember, the count is it's mine. It's in the promise. It's nested in the coroutine, right? And coroutine handle. This is what actually goes back to main. So if you think about it,
it goes back to main to be used in other functions and so on.
Yeah. So this is suspended. I call get. Value is 17. Co-yield value would return the value 17. I resume it. The plus 10 happens. but I'm returning the count. The count was 17 because the core yield set 17, but I'm resuming. So this plus 10 would happen and suspended, waiting for the next dot get.
I see.
Okay.
I mean, I probably see it like 40%, maybe. I understand 40%, I believe. But yeah, because I don't have to write the code myself to understand it fully. Or
I highly
fully.
recommend people to either take my repo or anyone else repo that has the same idea and just breakpoint. But
Okay.
the magic happens is that with core yield value, this yield value is being invoked. I'm setting 17 into count underscore, which is in my promise. Okay.
Yeah.
Which happens.
Right here,
it happens. It happens here, and I return this dot count. So 17 is returned. And since I have a resume, it's going to be resumed. This plus 10 would happen. Now, next time I do get, it's going to be 27. Why? Because when I do that get, it's here. What is the value here? Is 27 because it was plus 10 from the previous resume.
Yeah.
So set yield value would be setting count underscore, returning that to the caller. We do resume because that's what I have in that get. I have a resume. So it's going to be 27 plus 10, 37, waiting for the next time that I'm doing get. That's the whole idea.
And when you do get the next time, it'll be 37, no problem.
Yeah.
27 first and 37 and so on.
Yeah.
Okay, so it's just normal. It gets stuck into that loop until
I control
okay.
C, or I'm not. This is basically a dot get. There is no loop here. I have a generator and I can get more and more information. And I didn't like you could argue, hey, Kobe, I could do the same with a class.
Yeah.
Right? You basically I'm using a function here, but I could use a class, create an insert of this class, and just do dot get, and this dot get would just plus and whatever, plus 10 and yeah. But that's just an example of generators you can go and extrapolate it to other.
Yeah, of course.
But
like having it wait for 10 years or 20 years to do it.
Anything you can think of. Now, okay, now that we have this information, I think we can go into a bit more advanced. We are 6:20. Let's see how it goes. Hopefully you can stay a bit more because that's actually where the non-generator happens. I'll go there. It's mostly code. There is no actually explanation about, like, there's no text because you should be familiar with a lot of things now. So I'm using CPP. I'm using Conan. I used lib uring also in Conan, but the headers were not completely the same as my Ubuntu. So I use the package provided from the package manager of Ubuntu, but you can have liburing in Conan as well. This is how my CMake would look like with Conan. I use CRC, CPP just to simulate some work. I'm using FMT because I like the format. You can use more stuff in Conan as much as you want. Let's talk about synchronization first. Okay, so first of all, this is a synchronization, a synchronized, no coroutine, nothing special. We have a function that takes a UDP connection. The UDP connection is blocking. It's doing read on a buffer, and I have a vector that I'm computing CRC, whatever I got from the buffer. It's really simple. There is nothing special here. There is a UDP class that just read in a blocking manner, and it's synchronously happening. Okay, this is how the read would look like. It's really simple. There's an array for as an out parameter. You can make any other types. You can have it as a return value. This doesn't really matter. There is a receive from that is blocking, and then I'm just returning the result as is, and that's it. The result is as the size t, so I know how many bytes I wrote into this buffer. Very, very simple, nothing fancy here. A simple blocking function. Okay, so I have some helper structs that would help me when I start also dealing with coroutines. This struct has a buffer, has a CRC result, has the size of the buffer. Like the buffer is a kind of, I could use vector. I know it doesn't really matter. I just wanted to have more and more state just to illustrate some stuff. The CRC compute that does work is really simple. I just put it there in the slide just for you to understand there is no magic. It just compute CRC using CRC library that I pulled from Conan. It just this CRC of 16-bit, nothing very fancy, just updating and then returning the CRC results. Very simple and straightforward CRC. Okay, let's take a look at how main on a synchronous no coroutine would look like. I used two UDP sockets or two UDP classes. It's like if you think about like a UDP server. I have two connections. One is on 99 and 99. It's a tuple. This is an open range, just two of them. And I'm just making the connections, make unique of the connections, and then basically just reading the data synchronously. So it reads, it's blocking one, and then when it reads the data, the for loop would get to the next one. It's really synchronous read. So think about if I have 10 UDP connections and I have this for loop, I would start with the first one, waiting for this receive from to happen. When it happens, I go to the next one. So it's really serialized connectivity of reading from the socket. And I have 10. I have two of these. I can have 10. It doesn't really matter. I just have it as an example. I have just two UDP sockets, but I can have any UDP sockets that I would think, just to show you the async when we go to async. Is this obvious? This should be very, very simple. Nothing fancy here. Just synchronous receive from the socket. Okay, so let's add some more complexity using coroutines and Linux IO Uring, and going to the other block that I mentioned of Pavel. IO Uring is a very useful, though simple. The idea is really simple. You have a ring in the kernel that you can say, okay, I want to read to this file from this file descriptor, or I want to write to this file descriptor. This is the buffer to read from or to write to. And the kernel would provide me notifications when the read or the write, depends what I choose, was done. It's a very, very useful thing for us if we want to kind of speed up things. So IO Uring, which I think started from 5.x kernel. So it's very, very useful. And I'm going to use it to write stuff into files. In the blog that I mentioned, it's gonna show you read from file, but I'm gonna show you the writing. So this is the flow. I'm gonna prep the UDP socket, just creating the classes, not calling receive yet. And then I would have a coroutine that would have two co-await. One to read the UDP socket asynchronously, okay? And then I want to write to a file something again asynchronous. So the coroutine would be this part. And then I want to consume the IO Uring entries. This is basically where I listen to any kernel events. When it's completed, I can tell the part that is actually waiting for this completion that everything is good, and you can continue with the coroutine because this part is done. Now, remember I told you that I have two sockets as an examples, two classes, two UDP classes. The function that is my coroutine that I'll show you in a second, since I have two of these, I would have two copies of this function. So remember, if every time I'm running a coroutine, I'm creating this new instance of this coroutine frame, it's a new context. Okay, so since I have two sockets, remember that I have two copies of this coroutine frame, completely independent, which is really cool. Okay, this coroutine frame would have two wait, one to read the UDP socket, and then when we're done, we're gonna resume the coroutine frame. We're gonna ask the kernel to write, and when the kernel is done, we're gonna resume and we're gonna finish the coroutine frame. We can destruct the instance of the coroutine frame. And they are completely independent, but it looks like a function that is simple except the new keywords. Let's take a look at main. Main is really simple, nothing fancy, very simple to the other one. I have connections that I'm creating UDP connections. This connections is it's a vector of unique pointer. Nothing fancy. It's very similar to the async, just creating the classes. I'm not doing receive yet. Now I need to do some preparation for the IOU ring part, which I'm going to use. So there is an IOU ring class which is wrapping a lib uring. This lib uring is a wrapper over the raw kernel API that was written by someone which I can't remember the name. But if you go online, this is the one that you can get either from Conan or from the package manager. So basically, I have two tasks. These are the coroutine objects that I'm going to create, these tasks. I have two of these in a task vector. And what I'm doing is that I'm calling a coroutine function. This is where the whole magic happens with the UDP connect or specific UDP connection and specific uring. And I'm keeping the task that is generated, this coroutine instance that is being generated, I'm keeping in this vector. Why? Because I need later access to this to the context of this task. Now remember, I have two in my example. I just have two UDP connections. Every time I call read UDP write file async, I'm creating a frame. I'm creating this frame of coroutine. It's something that is not really visible unless you understand what's happening behind the scenes for with coroutine. So just lib uring wrapper is a very, very simple. It's just doing some housekeeping of the kernel. This is the most important. This ring is the most important part to communicate with the kernel API. I'm just putting that as a FYI how it's going to look like. The important part is how I'm actually creating the task and the promise. This should be very, very familiar because we did the same with the generator. The task is the one that is being generated by the coroutine function. This get return object is creating this task with this. And a few things. One is I have a result. Again, this is promise is my playground. I can put whatever I want. So I want to communicate back the result. What CRC I computed, maybe what is the buffer that I was reading. And remember, if I have two, I can have 10 of this UDP. For each of them, I have a different frame, a different context. Okay. Return value, which I call set return value, is where the result is communicated back, and then it's being propagated all the way to the caller. I think this is one of the things that kind of confusing a lot of. This is one of the magic because this is where the return value of the whole coroutine. There is a core return that you'll see that goes back to the caller. When I create a task, I don't want to be suspended. Compared to the generator, remember the generator, when I created it, when I called compute and I created the generator, I wanted to be suspended immediately. In the initial suspend, I wanted to suspend always. Here, no. I don't want this thing to be suspended, and I'll show you why. Because this is the specific use case. I don't want the coroutine to be suspended immediately when we're generating the task and the promise. Suspend never on the final. Suspend not really important here, but I need to provide it. Okay, so this was the promise type. Let's just collapse it and take a look at how the other thing looks like. There is a task that I'm actually generating. This is the task. This from promise. There are multiple ways to do that. This is one way. I showed you in generator a bit different way, but it's the same. I have a move constructor. I have a destructor that I can destroy the handle. I have a function done that I can query if the whole thing is done using the handle. This is the handle. This is one of the important things. This is the type def, but this is the handle. And I have the get result that I can actually get the result back, which is a struct with all my bookkeeping for this specific. Remember, I have two UDP connections, so I would have two copies of these tasks created by the runtime, right? The compiler would generate code for that. So I have two coroutine functions. Again, it's going to actually it's two coroutine awaitables. So this is the function, the main function that I'll show in the next slide. I have a co-await that of a read UDP socket. So I want to read UDP from UDP socket. I'm gonna run it. This is where the things needs to be. This is the design choice. What is the context? What is the thread context that you want to run this code? Remember, when I call coroutine function, when I create this is the read UDP write file async. This is coming from the main thread. Now, when I call co-wait read UDP socket, something would happen. There is code that's going to be executed. And then we're going to suspend this frame and main would continue. Now, the question is, where do I read the UDP socket? What is the context of the thread that I read? I made a design choice that I'm going to spawn a thread. I could do multiple ways. I decided that I'm going to spawn a thread that would call it. And I'm going to suspend the coroutine. This coroutine would be suspended until I decide to resume it. When I would resume it, I would resume it when the thread is done reading from the UDP socket. The thread would say resume the coroutine. The coroutine would continue to the next one, where we're going to write file with using co-await. Okay, and what happened with the writing of the file? This is actually interesting because this is where I tell the kernel, look, I want you to write to this file. I'm going to open a file. Here's the file descriptor. I want you to write this buffer to this file descriptor, and I'm suspending. Now the kernel has a thread that is going to do some stuff on my behalf, and in the main thread, I have a loop that checks the kernel status. Is it done? Is my data written to this file done? If it's done, I can pick it up and tell this waitable resume. It's going to be resumed, and the frame would be done, destroyed, and now I have a result, the full result of what is the CRC that I computed, what is the file that I was reading, anything that you can, not the file, the UDP data that I was reading, everything would be available to me at the end of the coroutine frame. When it's destroyed, I can have the result back. This is the result that I mentioned. So this is where I structured my code. It's, again, it's a design choice. here I have a thread that I'm spawning. I could have a thread pool instead, but I decided to do that. When I resume, from this thread, I'm done reading the UDP sockets and I resume, this part would be happening from the thread context of the resume. Then I do a co-wait, and when it's suspended, the thread would be gone. I used detached. I didn't want to do join, but it's a design choice. So how the coroutine would look like, okay? So the coroutine is this very simple function that is doing co-wait on reading UDP socket. So what happens behind the scene here is that I wrote code that would create a thread and start reading the UDP socket, and it's being suspended until the thread is done, resuming the coroutine would continue, and then suspended again here when I communicate with the kernel, kernel, I want you to write to this file descriptor. So I'm opening this file for writing, and I tell the kernel, okay, just write this file descriptor, this buffer. And in the main, because remember, what happened here is that the task is being created. We start the coroutine. When we do co-wait, main continues. So there is a for loop that calls read UDP write file async, in my case twice. So it's done very quickly because it goes here, it creates the awaiter, and goes back to the for loop of the main, right? And then another function is being invoked, read UDP file, and create another instance of this coroutine frame, another instance of this type. So I have these two types, and I would have two threads independently reading from the UDP socket and independently resuming their own task, their own frames to continue to the next level. The nice thing here, yeah, you can do the same with adding threads to this function, having conditional variables to wait and create. You can, instead of having a function, you can create an object with conditional variables inside. So conditional variables would be the ones that would synchronize your points. But this is without any conditional variables. I actually waiting here for a signal, a resume. It's like it's not really a signal, it's actually a function call, but there is no conditional variables involved here at all, but might resemble a conditional variable. Okay, so let's take a look at what happened when I'm actually calling in this loop twice read UDP write async. Again, get return object, by definition, this is the API, this is how the runtime would do. I'm creating a task and pushing it to the vector that keeps the task context because I need it later. I need the result later. The interesting part, this is the sea lion GDB, is that from this loop, I have this get return object, and it creates this task. And take a look at what the debugger shows me. I'm calling a function, and the debugger actually shows me the end of the function. It's kind of confusing because it's creating this task for me. So this is where there is a kind of it looks like a disconnect between what the debugger shows me and the actual source code. But just understand that what happened here is that task is being instantiated for us and returned back to the caller, which is in this case main, because I just called this read UDP write file async. Okay. For the UDP part, I have the result and I have the handle. Why I need the handle? It's very simple. When I do co-await something, this is the something. Read UDP socket. I do co-await of something, and I'm creating an instance of this something. This something is a class. I passing the UDP, and I keep the UDP. Okay. Now there is this operator co-await that I implement as an author of this awaitable. I'm writing that. So I have this awaiter, and as you probably remember, I have three functions beside the constructor. There are three functions that I need to implement. Am I ready? No, I'm not ready. Okay, I need to be suspended. I'm not ready. I want you to be suspended. This is where await suspend is being invoked because I was asked to be suspended. I'm not ready. Here's the coroutine handle that is being passed to me. This is the parameter that is passed to me by the compiler. So I basically this is very important because it's a context to the outer frame. Why I need that? I need that because I'm going to pass this handle to the thread that is going to read the socket in a synchronous manner because it's on a thread. Okay, and then we are suspended, and I'm passing the thread this data which I have here, the requested up, and it has a context. The context is a handle. I must pass the thread a handle of the coroutine because I want the handle to resume when it's done. If I'm not doing it, I don't have any way. I'm losing the one thing that enables me to control the coroutine. So I must hold this in order to do resume on this frame. When I'm resumed, I can return the result back. So basically, if you look at what happens here, when I am resumed, so when the thread is done reading from UDP and calling resume on the handle, I'm getting the result back. And the result is in the promise. This one, request data, which is this. It has the handle. I'm just aggregating the handle and the result. And remember, the result has the buffer, the CRC computation, all of that. I'm putting it back as a return value, and I'll use it later. So this is the first awaitable. How things would look like. You can see all these injections of that the compiler actually running, doing it for us, and the runtime would invoke. I have a thread that would do the read. This is where I spawn the thread. It's doing read. It's done. It's calling resume, and the frame is resumed. So this is how it's going to look like. Okay, and await resume is this one that returns back the result. Now I'm done with this part.
So hang on, that means you're handing off your handle to a separate thread. So the initial function gets called from a main thread, and then it awaits, it suspends, and your resume is getting called from a totally different thread, a worker thread.
Yes.
So it
Yes.
gets, so the remainder of this coroutine function gets called in the different thread context.
Yes, exactly.
So do you have, that means that implies that does CoRoutine API guarantee by itself that you have thread safe things, or is that something you need to be careful of when you're authoring your coroutine objects?
This specific, there is no guarantee. Like all the things that are related to multi-threaded holds. The thing in my specific case, if you look here, there is no at least I don't see any issues with race conditions, because what happens here is that main calls this function that would create this under the hood. Task is being created, it start running, but main doesn't do anything with it until the task is done.
Right. So this situation is safe because nothing else has contention.
Yeah,
you're not going to have two different threads trying to call resume. You've authored it such that only the worker thread will call it.
Okay. So remember, I have, because I called read UDP write file async twice in main. Go back to main here. Each invocation of this function would create another context, completely separate context, completely. and all the context lives in a different place. Okay, and I create this task, not me creating, but it's creating on my behalf. And now I'm going off to read from a UDP on a different thread on this specific frame. Now, I don't have two threads that actually using the same coroutine handle, because it's two different copies, it's two different instances. It's like I did, think about this read UDP write file async as like as a class that I did a new on this class, and I have a new instance of this whole frame with everything that involved in that, which means the whole context.
Right. So the
So
threads won't interfere with the worker threads won't
they're
interfere
not
with each
interfering with
other
it. They are
because they don't
completely
know
different.
about each
Yeah,
other.
they
But the
don't know
main
about each
thread
other.
could, you just authored it so that it doesn't.
Yes,
Okay.
exactly. Yeah, yeah. So go await read UDP, creating an awaiter, goes off creating a thread, go do your work, main continues, main resume to call again the same function, because that will be the second one. Same deal happens, another thread happens, waiting for incoming UDP data, and in the runtime, I have two parallel executions of this logic. Now the coroutine, actually two frames of coroutines are suspended until the thread is done. And I'm gonna jump. Let me see if I have. Let me see if I have the synchronously. Where do I put that? Which is important. I want to show you the resume of the. Okay, so the read sync. I don't have it. Okay, this is missing. So the read sync is the same as what I showed you before. Just read from UDP, but it's actually going to have another line that says handle dot resume. Okay, and then the whole thing would be resumed. Which is basically, this is what I kind of didn't put the code, but this read sync, which is a function, just a regular function that reads from UDP, eventually has, when it's done, it's calling resume. Why? Because I passed the handle to this function to the API of the through the API of the thread here, because I put data.handle and I pass it as a reference, and I'm good. Now, lifetime. The awaiter lifetime holds. Look, I put a ref to data to the thread I did detach. It holds. It's not destroyed. It's destroyed at the end. Like if you put breakpoints of printfs in the awaiter destructor, you'll see that. So that's important. Only at the end of the frame. In this case, exactly, especially. Okay, let's go to the next one. The next one is as I mentioned, also simple, but it doesn't involve any threading that I create. I'm actually taking advantage of kernel doing the work on my behalf, and I'm just in the main. I'm just spinning and waiting for completion. When I have completion, I can tell the coroutine, yeah, resume, which is gonna continue and do the co-return and complete the function. So co-await write file awaitable gets a file descriptor, gets the result, because the result has the buffer that I want to write to the file. I have the uring context. I have all of the stuff, all the boilerplate code for me. The important part is the await suspend. So when I do co-await write file awaitable, I'm suspending, and I have opportunity to do some stuff. What do I do? First of all, I take the handle and stick it to a specific struct that I wrote, this struct. Okay, I need the handle. I need the handle. And then the kernel has a very nice API where I can say, okay, look, for this specific session, when I want you to write into this file descriptor, I have a cookie for you. Please, it's an opaque cookie. Give it back to me when you are done. There is an API to get it back. Why? I need this whole thing back because I need a reference back to my coroutine handle so I can resume it. So, and there is a status code, success or failure of writing to the file that I can obtain from the um, kernel operation. Just a second awaiter. So if you think about it, I have two frames. Each of them has two awaiters, a task, and a promise inside. So that's basically all the big players of this architecture. Again, here's what happened when you do co-await. The awaiter is constructed. It's just an example what happened when you write co-await. This awaiter and same deal for the other awaiter are being instantiated with this operator co-await. And this is how it's going to look like. There is for main, I'm read filed, and then there is a co-await and the awaiter, and looks very ugly, like this whole function names which are injected by the runtime. Okay, so from the main, again, I'm reading, calling read UDP write file async, and I'm not ready, so I'm calling suspend. I already talked about it, just another example. That's basically it. I have a thread that doing the UDP, resuming on the thread context of this specific thread that I created for each frame. I'm continuing until I'm hitting the next co-await, asking the kernel to do a write on our behalf, and suspending. Now I need to wake up the whole thing. So here is the code. It's pretty much a boilerplate code that it's very similar to what you would see in Pavel's Pablo a blog. There is one, by the way, there is one small difference. This was missing from the, if you try out, this was missing from the blog. This is not going to work without this magic line. You need to tell the kernel that you want this thing to be submitted. Just a small typo in the blog. So I have a logic where I'm waiting for the task, and the task is a whole frame of the coroutine. Remember this whole function. I'm waiting it to be done. Remember I had this done function. I'm waiting it to be done, and then once it's done, I can go and do whatever remember I have this get result. I can just get result. Whatever I put there is in result, I put CRC. That's fine. I can have everything. This is my opportunity to write any functions that I want in the task class that expose result back to me. And this is just regular code in main. How all done would look like? All done is really simple. I'm waiting for all of the tasks are done. And what I do is I'm blocking on the queue, the kernel queue, waiting for one element at a time. If I have something, I consume it. How do I consume it? This kind of a boilerplate code. The important part is the following. So remember, there is a coroutine that is suspended on the second co-await because I told the kernel submit. The thread is gone because I'm suspending. There is no thread anymore. At this point, there is only main thread. We wake up here. If everything goes well, we wake up here. The file was written. We tell the kernel, okay, what was the result code? Okay, good result code we have. And we can now resume. Remember, I kept the handle. I can resume the coroutine to completion to be done. Okay, and when it's done, so all done. When it's done, I'm doing this while I can go here and start querying the results, which is basically just my struct in as part of the task. That's part of the promise. I just query because I know that the coroutine, the whole function that had two core weight is completely done. This is the magic where resume happens here because I have the context. So remember, the handle that I get in the core weight, this handle is super important. This is where you need to keep it somewhere because this is where you control the future flow of your coroutine that is being suspended, because this is my opportunity to do something before it's really suspended and the code continues to like a different flow, in this case main. So it's really important to keep this handle somewhere to be used. And again, you can do whatever you want with that. This is just one implementation. Um, this is basically my last slide. I don't know how many people managed to uh, keep up, and I actually, it took me 2 hours. This is the first time I'm doing it. It is a lot. It's 60 slides. But hopefully this is much easier now to understand coroutines. Hopefully, if not, give me feedback where you want more stuff to be explained, and I'll change my slides for if there is a next time to somewhere. I'll do that.
Well, I would like to, I don't know, see like a real example of something something usually used in the industry. I don't know what exactly, because this is a new concept to me.
Yeah, I
But yeah,
agree. I agree.
mhm.
It's new to me. Basically, it's new to me as well, and I need to digest it and see how it's a paradigm shift. Instead of using conditional variables and
Mhm.
classes that have that when we explicitly maintaining the instance and the flow, and we signal each other and we do future and promises to signal the result. This is a very different paradigm. It's a different
Wow.
shift, right?
Yeah. Yeah, interesting. I see what you're saying now. So we won't need conditional statements in the future if
Yeah,
we're using
and
coroutine.
yeah,
Ah,
if you Google for coding, there is I think Rainer Grimm had
Rainer Graham.
maybe one time he had some example of, here's how I can do this whole condition of variable synchronization without condition variable, but using coroutines instead.
Coroutines. Oh, that's very interesting, man. Thank you so much. I hope you understood it better now because you explained it using the Feynman techniques. I
Yeah,
hope you digested much better.
yeah.
And thank you for this. Really, really valuable.
Thanks everyone. Thank you for sticking in and to the rest of the talk, and have a good rest of your day, your night, not whatever the time zone you are in. Thanks everyone.
Yeah, thank you, Kobe. Thank you very much.
Thank
Thanks.
you.
Thank you, Kobe.
Have a
Thank you.
great night.
Good night.
Thank you.